We're moving into the big leagues, mastering rational function analysis. This is the bread and butter for my scientific and math stream champs. Step 1. The foundation. Look at our function f of x. We got a quadratic over a linear expression. First things first, look at that denominator, 2x plus 4. It can't be 0, right? That's why our domain is everything except -2. We're going to calculate the limits at the boundaries, and boom, that's how we find our vertical asymptote at x equals -2. It's like a wall the function can never cross. Step 2, the movement. Now, look at the derivative f prime of x. I've already laid out the formula for you. We're going to study the sign of this bad boy to see where the function is climbing and where it's sliding down. We've got extreme values at x equals -5 and x equals 1. Those are our peaks and valleys, folks. Pay attention to that table of variations. It's your GPS for the graph. Step 3, the oblique asymptote. All right, here's the deal. Since the degree of the top is exactly 1 higher than the bottom, we're looking at an oblique asymptote. We're going to prove that as x heads to infinity, our function hugs the line y equals 0.5x minus 4. It's all about that long-term relationship. Step 4, the tangent. Precision is key here. We're going to write the equation for the tangent line t, specifically at the point x equals -1. This tells us exactly how the curve is leaning at that very moment. Step 5, the masterpiece. This is where the magic happens. We take everything, the limits, the asymptotes, the extreme values, and the tangent, and we sketch the curve c of x. If your analysis is right, the graph will practically draw itself. Step 6, the boss level. Finally, we're doing a graphical discussion. We're going to look at f of x equals 0.5x plus m and f of x equals m. When moving lines and seeing how many times they hit our curve, this is where we separate the students from the masters.
Look at the screen, my dear students. This is our star of the show today, a rational function. Forget about the easy stuff. We are dealing with f of x equals x squared minus 6x minus 7 over 2x plus 4. First things first, look at the domain. See that? It's defined on all real numbers except for -2. Why? Because in this neighborhood, we don't divide by 0. That -2 is a no-go zone, a wall that our function just can't climb over. We call it r except for -2. Keep that in mind because it's going to be the most important detail when we start drawing. Now, let's talk about the mission. This is our roadmap, our game plan. We aren't just guessing here, we are being surgical. 1. Analyze limits and asymptotes. We need to know how this function behaves when x gets huge or when it creeps up on that forbidden -2. Is it going to fly up to the clouds or dive into the basement? We're going to find out. 2. Derivative and variations. This is where the real magic happens. We're going to find the pulse of the function. Is it growing? Is it shrinking? Where are the peaks and the valleys? The derivative tells us everything. 3. Slant asymptote and position. Since the degree of the top is 1 higher than the bottom, we've got a slant asymptote coming our way. It's like a guide rail for our curve as it heads off to infinity. We need to know if our graph is sitting above it or below it. No guessing allowed. And finally, look at the goal. This is the prize at the end of the tunnel. 4. Plot the curve, CF. We're going to take all that data and put it on paper. It's going to be a masterpiece, I promise you. 5. Parametric discussion. We'll spice things up and see how things change when we throw in some extra variables. 6. Composite functions. We'll wrap it all up by seeing how this function plays with others.
Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow.
The toolkit, essential concepts. Think of this as your heavy-duty utility belt. First off, let's talk limits and asymptotes on the left. When you're dealing with rational functions and x is headed all the way to infinity, don't get distracted by the small numbers. Focus on the big dogs, the highest degree terms. It's all about that ratio, an over bm. And look at that vertical asymptote rule. If the function explodes to infinity as x approaches a specific value a, then boom, you found your vertical asymptote at x equals a. It's like a wall the function just can't cross. Now move your eyes to the center, differentiation rules. This is where the real magic happens. We've got the quotient rule for when functions are stacked on top of each other. Remember the rhythm, u prime v minus uv prime,
all over v squared. Don't mess up that minus sign or you're going to have a bad day. And right below it, the chain rule for composite functions. When you have a function u raised to a power n, you bring that n down, keep the u to the n minus 1, but, and this is the part where people trip up, you must multiply by the derivative of the inside, that u prime. It's the secret sauce, don't forget it. Finally, look over to the right at quadratic equations. This is an old friend, but a powerful one. For any equation in the form ax squared plus bx plus c equals 0, you gotta check the discriminant, our good old friend delta. If that delta is greater than 0, you're in business. You've got two distinct roots, 2 points where that parabola hits the axis.
Boundaries, limits, and asymptotes. Now, look at me. This isn't just math. This is about understanding how things behave when they get pushed to the edge. Don't blink, because this is where the magic happens. Take a look at the slide I've got up here. We are breaking this down into 2 parts, the calculations, the how-to, and the geometric insight, the what it actually looks like. First off, let's talk about limits at infinity. Imagine x is traveling way out, far beyond the city limits, heading towards positive or negative infinity. Look at the math here. When we take the limit of f of x as x goes to negative infinity, we focus on the strongest terms. That x squared over 2x simplifies down to just x over 2. So if x is a massive negative number, the whole function is diving deep into the basement, negative infinity. And if x is headed to the moon, positive infinity, the function follows right along. It's straightforward, it's logical, and it makes sense, right? But now, pay close attention to point number 2, the singularity. This is the trouble spot at x equals negative 2. In our neighborhood, we don't just ignore trouble, we investigate it. When we plug negative 2 into the top part, the numerator, we get a solid 9. But look at the bottom, the denominator, it's crashing, it's approaching 0. Now, you know the rule, you can't divide by 0. So we look at it from both sides. From the left, that's the negative 2 minus, the function is plummeting to negative infinity. From the right, the negative 2 plus, it's skyrocketing to positive infinity. It's like a roller coaster that breaks apart right at that line. Now, look over at the geometric insight on the right side of the screen. This is the visual, the soul of the math. See that dashed orange line at x equals negative 2? That, my friends, is the vertical asymptote. Think of it like a giant glass wall in the middle of the road. The function gets closer and closer. It's screaming toward it. It wants to touch it so bad, but it never, ever will. It just hits that barrier and explodes up to the sky or down to the ground. You see that? That's the power of limits. We can predict exactly where the no-go zones are. I want you to feel this, class. Don't just memorize the numbers. See the wall. See the behavior.
The engine of change, the derivative, and specifically, we're gonna master the quotient rule. Don't let the name scare you, it's just a tool, and I'm gonna show you exactly how to swing it. Here, we have a function, f of x, which is a fraction. We've got one function, u of x, sitting on top of another one, v of x. When you see a setup like this, you gotta think quotient rule immediately. Forget about everything else, this is your go-to move. Step 1. The setup. Look at how we break this down. We identify our players. The numerator, u of x, is x squared minus 6x minus 7. Its derivative, u prime of x, is 2x minus 6. Easy money, right? Now look at the denominator, v of x equals 2x plus 4. Its derivative, v prime of x, is just 2. We've got our ingredients ready on the counter. Now let's cook. Step 2. The substitution. Now pay attention, because this is where the discipline comes in. We use the formula, derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Look at the substitution line. We're just plugging our pieces into the machine. We have 2x minus 6 times 2x plus 4, then we subtract 2 times the original top part, x squared minus 6x minus 7. And don't you dare put that whole bottom part, 2x plus 4, in a square. Step 3. Expansion and simplification. This is the grind, people. This is where you show me you've got that focus. We expand the numerator. Look at the blue and orange terms. We multiply them out. FOIL method, remember? We get 4x squared plus 8x minus 12x minus 24. Then we distribute that negative 2 into the second parentheses. Watch those signs. A negative times a negative is a positive. Don't let that trip you up in the heat of the moment. We get negative 2x squared plus 12x plus 14.
Now look at the numerator lines. We're just cleaning house. Combine the like terms. 4x squared minus 2x squared gives us 2x squared. The x terms gives us 8x and the constants give us negative 10. We're almost there. Step 4, the final result. Look at that beautiful box at the bottom. We factor out a 2 from the top to make it look sharp. We simplify the denominator by factoring out the 2 from inside the square, which becomes a 4 outside. We cancel out what we can, and boom! F prime of x equals x squared plus 4x minus 5 over 2 times x plus 2 squared.
Now, eyes on the board, everyone. We are talking about enamelizing variations, and specifically, we're looking at the signs of f prime of x. This is where we find out exactly how our function is moving. Is it going up? Is it going down? The derivative is going to tell us the whole story, so pay close attention. First, let's look at the logic. Look at the derivative we have here. The denominator is 2 times x plus 2 squared. Now, I want you to use your heads. Anything squared is what? Exactly, it's always positive. So that denominator isn't going to flip any signs on us. It's solid. This means the entire sign of our derivative, f prime of x, depends strictly on what's happening upstairs in the numerator, x squared plus 4x minus 5. So, let's get down to the calculation. We need to find where that numerator hits 0. We solve x squared plus 4x minus 5 equals 0. We use our old friend the discriminant, delta. We do the math, 4 squared minus 4 times 1 times negative 5, which gives us 16 plus 20 equals 36. That's a beautiful number, right? A perfect square. That gives us two clear roots, x1 equals negative 5 and x2 equals 1. These are our turning points, the spots where the action happens. Now, look at this number line I've laid out for you. This is the map of our function's behavior. To the left of negative 5, we are in the positive zone. The function is climbing. Between negative 5 and 1, things get interesting. Notice that double bar at negative 2? That's our undefined point. You can't touch that. It's a gap in the road because it would make our original denominator 0. On both sides of that undefined point between our roots, the sign is negative. The function is taking a dip here. And finally, once we pass x equals 1, we're back in the positive territory. We're heading back up.
Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow.
Look at the screen right here. This is what I call the blueprint. In the world of calculus, we call it the table of variations. If you want to understand a function, you don't just look at it. You read its soul through this table. This is the roadmap that tells us exactly where we're going, where we're stopping for a break, and where we're heading off the rails. First, look at that top row, the X row. This is our domain, our timeline. We're traveling from negative infinity, minus infinity, all the way to positive infinity, plus infinity. But notice those specific stops, minus 5, minus 2, and 1. Those aren't just random numbers. Those are the main events of our function. Now pay close attention to that double vertical line at x equals minus 2. You see that? That's a no-go zone, my friends. That tells us the function is not defined there. It's a break in the road, likely a vertical asymptote. We don't touch that line. Next row, f prime of x, the derivative. This is the engine. From minus infinity to minus 5, the derivative is positive, plus. What does that mean? It means the function is climbing the skyscraper. It's going up. At x equals minus 5, the derivative is 0. Boom! The engine pauses. We've reached the top of the hill. Then from minus 5 to minus 2, the sign flips to negative, minus. We're sliding down, heading back to the subway. Now look at the bottom row, f of x. This is the actual path. See that arrow pointing up? We start at minus infinity and climb all the way to minus 8. Because the derivative was 0 at x equals minus 5, we found ourselves a local maximum. That's the peak of our first mounting. After that peak, we drop back down toward minus infinity as we approach our no-go zone at minus 2. But wait, there's more. On the other side of that double line, we start fresh at plus infinity. The derivative is negative, minus, so we are dropping fast. At x equals 1, the derivative hits 0 again, another flat spot. Look at the value, minus 2. Since we were going down and now we're about to go up, this point is our local minimum. It's the bottom of the valley. Finally, from 1 to plus infinity, the derivative is positive again. We're back on the rise, heading straight for the clouds at plus infinity.
The hidden line. It sounds like a mystery novel, doesn't it? But it's even better. It's the slant asymptote. Sometimes a function doesn't just settle for a flat horizontal line. It wants to follow a path, a slope, a direction. Now follow me closely. Look at the process on the slide. We have a function f of x that looks a bit complicated. To find this hidden line, we perform a division. We take that quadratic expression, x squared minus 6x minus 7, and we divide it by 2x plus 4. It's like we're peeling an onion to see what's really going on inside. And look what happens when we do the math. Boom! We rewrite f of x into two very distinct parts. Look at that big blue arrow pointing to the result. F of x equals 1/2 x minus 4 plus 9 over 2x plus 4. I want you to see what I see. This is the identification phase, and it's beautiful. We've got the linear part, which is y equals 1/2 x minus 4. This is our hidden line, the soul of the function's behavior at the extremes. Then we have the remainder part, that 9 over 2x plus 4. Now, why does this matter? Look at the verification step down there. I'm telling you, this is where the magic happens. We take the limit of that remainder as x goes to infinity. Whether x is getting huge on the positive side or huge on the negative side, that fraction, 9 over 2x plus 4, is going to get smaller and smaller until, poof, it's basically 0. When that remainder vanishes at infinity, it means our function f of x is getting closer and closer to that line, y equals 1/2 x minus 4, without ever quite touching it. So what's the bottom line? The conclusion is right there in the box. The line, delta, with the equation y equals 1/2 x minus 4 is officially our slant asymptote at plus or minus infinity.
Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow.
Precision placement, relative position. This is where the magic happens. We don't just want to know where the function is going, we want to know exactly where it sits compared to its asymptote. Is it dancing above the line or hiding below it? We're going to find out right now, and I promise you, it's easier than finding a good bagel in Brooklyn. Check out the concept here. To figure out the relative position, we analyze the sign of the difference. We call it d of x, which is just our function f of x minus the equation of the asymptote, y delta. In this specific example, we've calculated that difference to be d of x equals 9 over 2x plus 4. Now use your heads. Look at that numerator. It's a 9. That's a positive constant. It's not changing for anybody. So the whole sign of this fraction depends entirely on the denominator, 2x plus 4. Look at this table I've put together for you. This is our roadmap. The first interval, negative infinity to negative 2, in this neighborhood, when you plug in those numbers, 2x plus 4 comes out negative. Since we have a positive 9 divided by a negative number, the whole result is negative. What's the verdict? The curve is below the asymptote. You can see it in that first little sketch at the bottom. The solid curve is ducking under that dashed line. It's staying low. The second interval, negative 2 to positive infinity, now we cross over that boundary at negative 2. In this zone, 2x plus 4 turns positive. Positive divided by positive, that's a plus sign all day long. So the curve is above the asymptote. Look at the second sketch. The curve is rising up, sitting proud right over that dashed line. See those arrows at the bottom? They tell the whole story.
If the difference is less than 0, the curve is under the line. If it's greater than 0, the curve is over the line.
Anchors. And let me tell you, in the world of functions, anchors are everything. Think of them like the steel beams of a skyscraper in Midtown. They hold the whole structure together so you know exactly where you're standing. We're focusing on two major players here, tangents and intercepts. Check out the left side of the slide. We're looking for the tangent, t, at x equals -1. Now, don't let the notation scare you. You're tougher than that. Look at that formula. Y equals f prime of -1 times x plus 1 plus f of -1. It's a classic point-slope variation, and it's beautiful. We did the heavy lifting for the calculations. F of -1 gives us 0, and the derivative, f prime of -1, that's the slope, the hustle of the line, is -4. Put it all together, simplify it, and boom, you get y equals -4x minus 4. That's your tangent line, sharp and precise, kissing the curve at exactly that point. Forget about it, it's perfect. Now pivot your eyes over to the right side. We got to talk about axis intercepts. This is where our graph actually meets the streets, the x and y axes. First, the y-axis. This is the easy win, folks. You just set x to 0. When we plug that in, we get f of 0 equals -1.75. So our point is 0, -1.75. That's where the graph crosses the vertical line. But wait, look at the x-axis. To find where we hit the pavement horizontally, we set the numerator to 0. We've got a quadratic there. X squared minus 6x minus 7 equals 0. You solve that, and I know you guys can do quadratics in your sleep by now, and you get two roots, x equals -1 and x equals 7. That gives us two solid points, -1, 0 and 7, 0.
This graph of CF is the ultimate test of everything we've learned so far. First off, look at that bold red dashed line standing straight up at x equals -2. That's our vertical asymptote. See how the blue curve is trying so hard to reach it, but never quite gets there? It's like it's hitting an invisible wall. That tells us something huge about the domain of our function. It's a no-go zone. Now look over at the left side of that wall. We've got a smooth curve reaching a peak. That's our local maximum right there at the coordinates -5, -8. It's the king of that hill. But then, look what happens on the right side of the asymptote. The curve drops down, hits a floor at 1, -2, which is our local minimum, and then starts climbing again. But wait, there's more. See that blue dashed line stretching diagonally across the grid? That's the slant asymptote with the equation y equals 0.5x minus 4. As x heads out to the far right, our function CF starts following that line like it's a guided path. It's all about the long-term behavior, folks. And check out the intercepts. Our graph kisses the x-axis at 2 points, -1, 0 and 7, 0. It crosses the y-axis down at 0, -1.75. Oh, and don't miss that sharp black line slicing through at -1, 0. That's our tangent t, y equals -4x minus 4. It tells us exactly how fast the function is dropping at that specific moment.
Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow.
Last time, we spent a lot of time breaking down how to find those asymptotes and identifying the local extrema of our function. We talked about where the function climbs and where it takes a dip. Now, we're going to take all that hard work and put it into action with a real graphical discussion. This is the moment where we see how many times a horizontal line, y equals m, hits our beautiful curve. It's like we're scanning the graph from bottom to top. You ready? Let's get into it. Take a look at this gorgeous graph on the screen. We've got our blue curve, CF, doing its thing.
You can see that vertical asymptote in red at x equals -2. Don't even think about crossing that line. And we've got our slant asymptote, y equals 0.5x minus 4, guiding the function as it stretches out to the horizons. Now, look at that red horizontal line labeled y equals m. Imagine we're sliding that line up and down the y-axis. Here's the play-by-step breakdown of what happens. 1. When m is less than -8, m less than -8. Look at the bottom left. Our horizontal line hits the blue curve in 2 different spots, so we've got 2 solutions. Easy start, right? 2. When m hits exactly -8, m equals -8. Boom! We're right at the peak of that local maximum. The line just kisses the curve at one single point. That's one solution, the max. 3. The dead zone, -8 less than m less than -2. Now look at that gap in the middle. If our line m is between -8 and -2, it doesn't touch the blue curve at all. It's empty space, folks. We call that no solutions. 4. When m hits exactly -2, m equals -2. We've reached the bottom of the upper branch. The line touches the local minimum. Just like before, that's one solution, the min. Finally, when m is greater than -2, m greater than -2. As we keep sliding that line up towards the sky, we start hitting the curve in 2 places again, one on the left of the minimum and one on the right. That gives us 2 solutions.
Look at the board here. We're talking about the oblique discussion. Now, don't let the name intimidate you. It's just a fancy way of seeing how our function f of x interacts with a family of lines that are slanted. Specifically, we're looking at lines that look like y equals 1/2 x plus m. You see that m right there? That's our shifter. It moves the line up and down the y-axis, but the slope? The slope stays exactly at 1/2. It's like a fleet of cars driving parallel on the highway. Geometric insight, the big picture. Check out this graph I've got for you. You see that beautiful blue curve, c of x? That's our function. And you see that dashed line cutting through? That's the slant asymptote, y equals 0.5x minus 4. Our mission is to see where the lines y equals 0.5x plus m hit our curve. Since the slope is the same as the asymptote, these lines are all parallel to it. It's like we're scanning the entire graph with a ruler held at that specific angle. The algebraic proof. Let's crunch the numbers. Now, follow me here. Don't blink. To find where they meet, we set them equal to each other. We take our function, 1/2 x minus 4 plus 9 over 2x plus 4, and we set it equal to our moving line, 1/2 x plus m. Look at how beautiful this is. The 1/2 x on both sides? Forget about them. They cancel out. What are we left with? 9 over 2x plus 4 equals m plus 4. This is the heart of our discussion. This equation tells us exactly how many times our line and our curve shake hands. The discussion results, breaking it down. I want you to focus on these 2 cases because this is where the magic happens. Case 1, m equals -4. If m is exactly -4, our line becomes the slant asymptote itself, y equals 0.5x minus 4. Now, look at the graph. Does the curve ever touch that dashed line? Never! Algebraically, if you plug in m equals -4, you get 9 over ... equals 0, which is impossible. You can't divide 9 by something and get 0. So, 0 solutions. The curve and the asymptote are like 2 people who like each other but never actually meet. Sad, right? But that's math. Case 2, m not equal to -4. As soon as m is anything else, even just a tiny bit higher or lower, the line shifts. Whether it's the solid line you see passing through 7, 0 or any other parallel line, it's going to pierce through one of the branches of our curve. In this case, we get one unique solution. Take a look at those points I've marked for you. The intercepts, the minimum at 1, -2, and the maximum way down at -5, -8. Everything connects. We're seeing how this function lives and breathes in relation to these slanted lines. Before we move to the next slide, let's keep this momentum going.
Before diving into what's next, don't forget to subscribe to stay updated with all the new content. If this helped you, give it a like, share it with someone who might need it, and leave a comment. Your questions and feedback help everyone grow.
Look at the screen. Don't blink. We are looking at a very specific, very powerful composite. H of x equals f of x squared. Now, I know what you're thinking. Professor, it's just a square. But hold your horses. This is where the calculus gets beautiful. First off, let's talk differentiation. How do we find the slope of this bad boy? We use the chain rule. Forget about the noise. Just look at the formula. H prime of x equals 2 times f of x times f prime of x. See that? The power comes down, you keep the function, and then this is the secret sauce. You multiply by the derivative of the inside. It's a team effort. Now, pay close attention to the sign analysis logic. This is the New York Minute shortcut I want you to master. Since the number 2 is always positive, it doesn't change the sign. That means the sign of our derivative, h prime of x, is simply the product of the signs of f of x and f prime of x. It's like a dance. If they're both in sync, both positive or both negative, the result is positive. If they're clashing, it's negative. Simple as that. Let's break down this summary table together. I want you to see the story it's telling. First off, interval negative infinity, negative 5. Look at the first column. F of x is negative, but f prime of x is positive. What's a negative times a positive? You got it, it's negative. So h prime of x is negative here. We also see a max point noted there. Keep that in your back pocket. Interval negative 5, negative 2. Both f of x and f prime of x are negative. Negative times negative, boom, positive. H prime of x is climbing up. Interval negative 2, negative 1. Look at this red zone. We've got a vertical asymptote happening. F of x is negative, f prime of x is positive, so h prime of x stays negative here. The function is diving down near that asymptote. Interval negative 1, 1. Back to both being negative. H prime of x is positive again. We've got a root at negative 1, so pay attention to where the graph hits the floor. Interval 1, 7. Now we're in the green. Both f of x and f prime of x are positive. Positive times positive is positive. H prime of x is moving up, and we hit a min point in this stretch. Interval 7, infinity. Finally, look at the end. Both are negative again, so h prime of x remains positive.
Now look at the screen, my champions. This right here is the synthesis and key takeaways. This is where we bring everything home. We've been working hard, crunching numbers, and now we're going to see how all those pieces fit into one beautiful logical puzzle. This is the roadmap for mastering rational functions. First off, let's talk about boundaries. Look at point number 1. In this game, you gotta know where you can and can't go. Limits are the real deal. They define the box for our function. When you calculate those limits, you're revealing the vertical asymptotes. It's like setting the stage before the show starts. You're marking the lines that the function will never cross. It's about structure, folks. Moving right along to variations. Check out number 2. This is where the derivative, f prime of x, takes the wheel. I'm telling you, the derivative is the boss. It dictates the direction. Is our function climbing up to the top of a skyscraper, or is it diving down into the subway? Whether it's increasing or decreasing, f prime of x gives us the play-by-play. You follow the derivative and you'll never get lost. Now look at number 3, geometry. This is where we get a bit more sophisticated. We use polynomial division, and don't you dare give me that look. It's easier than it looks. This division is the secret key that uncovers the slant asymptote. It gives our graph that sleek diagonal flow. It's the skeleton that holds the whole geometric shape together. And finally, point number 4, precision. You want your work to look professional, right? You want it to be sharp. Tangents and intercepts are your anchors. They pin that curve down exactly where it needs to be. Without them, you're just guessing. With them, you're an artist. They ensure your drawing is accurate and reflects the true soul of the function. Look at that final note at the bottom, because it's the most important thing you'll hear today. Mastering a rational function requires bridging the gap between algebraic calculation and geometric interpretation.